right. So this lecture and lecture 32 are going to close out the chapter on dimensional analysis. Up to this point, we've discussed the Buckingham pi theorem, how this allows us to determine that some as of yet unknown functional relationship between dimensional variables can be reduced to a unknown functional relationship between a smaller set of dimensionless variables. And we sort of motivated this through some examples using pipe flow, etc. This lecture and the next one are going to be kind of taking that knowledge and applying it, in this case, using what we call experimental correlations, and in lecture 32, doing what we call model scaling. So our goal today is, first, our goals, I should say. We want to understand how to represent relationships between dimensionless groups. Represent. So between pi terms, all right. We want to perform. Actually, you know what? We'll apply experimental correlation rather. To estimate, in this case, we're going to return back to our pipe flow example at some point. And we're going to kind of loop back to, we started on this in the last lecture, discussing the sort of these common recurring pi terms that show up in fluid mechanics. And really what they come from is if we were to apply dimensional analysis, right? So applying dimensional analysis on the Navier-Stokes equations. So we're going to skip over the kind of the derivation step of actually doing the dimensional analysis and non-dimensionalizing Navier-Stokes. But we'll, at this point, we've sort of seen how we can use that method of repeating variables, right, to non-dimensionalize a set of variables to come up with pi terms. And if we did that with Navier-Stokes, what we'll see is that there are some common pi groups that fall out of that. So at this point, pretty firmly established that dimensional analysis gives us the tools to reduce a set of equations down to a smaller subset of pi terms. And this, right, I'm hypothesizing or I'm positing that this makes experiments easier. But how much easier, or I should say how easy they are after applying dimensional analysis, really still depends on the number of pi terms that we have. So the ease of experiments, or I should say the ease of use of experimental data, the number of pi terms. So we're going to say, for example, to start off with, the easiest case is if we have a single pi term. That is, if our Buckingham pi theorem, okay, this is with k minus r equal to 1. In this case, right, the idea is we'd end up with, we go from, u1 equals some function of u2, etc., uk. By applying the method of repeating variables, we end up with pi1 equal to some function of nothing. And we'll do an example here in just a second. So if we end up with something that is a function of nothing, what does that mean that something is? Constant, right? So this is saying that pi1 is a constant value. So as an example of a case like this, let's consider example like a body falling through a vacuum. So let's consider, right, we've got some arbitrarily shaped body. We've got gravity acting vertically downward. This body we'll assume is solid. It's got some characteristic length, right? Some characteristic height maybe, and it has some, right? It has a density of rho. And we're interested in, basically, given a certain amount of time, we're interested in knowing how far, if we release this thing, we're holding it, and we release it, we want to know what functional relationship we can assign to the distance fallen, right? So let's go through the kind of the rigmarole of the dimensional analysis on this. We're saying that y, right, which is the distance fallen, is a function of what variables here? Think of, right, basic dynamics, kinematics. In a vacuum, the only two things that are going to affect the distance fallen are going to be what? I heard gravity. Yep. And then the time elapsed since it was released, right? Note if we weren't assuming this to be in a vacuum, if we were dealing with releasing this in something where air resistance was a factor, then we would need to include things like the density of the body, the density of the surrounding air, viscosity, the actual dimensions of the body. But since we're boiling this down to that really simple kind of classical case where we don't worry about air resistance, these are the only two things that factor in. Okay, so that was step one, right, of our dimensional analysis process, which is list all important variables. Step two is to express dimensions. So we've got y, right, which has dimensions of length. We've got time, which has dimensions of time, obviously. And we've got gravity, which is length time to the negative 2. Step 3 is determine the number of pi terms. So we have to figure out k, r, and then k minus r. So if we look at our original equation, right, how many dimensional variables are there? 3. Y, g, t. Okay. We've got k equal 3. How many reference dimensions are present in our k variables? We've got length, we've got time, mass doesn't show up, temperature doesn't show up, so we've got 2. Okay, so this is telling us then that k minus r is going to give us only one pi term.
So now step 4 is select repeating variables. Okay. Now remember, the rules for repeating variables is that they have to have independent combinations of dimensions, and there have to be r of them. So in this case, since r equals 2, we need 2 repeating variables. I suggested before that we pick sort of the simplest ones. In this case, that would be y and t. That's we could go ahead and do it that way. I think. Oh, sorry, no. We're not going to pick y and t. We're going to pick g and t because generally you don't want your dependent variable to be one of your repeating variables. Okay, so whatever's on the left-hand side, you want to leave alone. So g and t selected as repeating variables. And then, right, step 5 is basically, we only go through this once. We have one pi term to form. It is y times g to the a times t to the b. Should have dimensions of, right, length a time to the negative 2a time b. So length time 1. We want this to be length 0 times 0. All right. So we got 1 plus a equal to 0. And for time, negative 2a plus b equal to 0. So from here we have automatically the a is equal to negative 1. We plug that in down here. This becomes a 2. So 2 plus b is equal to 0. So we get that b has to be equal to negative 2. So this is telling us that our pi term then, pi 1, is equal to, right, y over gt squared. And then we can write step 6 is repeat this for any other non-repeating variables. In this case, we only have the one non-repeating variable, so we're done. Step 7 is check, make sure that it is actually dimensionless. We'll go ahead and, so we've got length over time squared times time squared. So we can see by inspection, in this case, we're going to end up with a dimensionless quantity. And then we'll skip right on down to step 9. Right? So step 6 through 8. And step 9 is basically look at our functional relationship and determine what it means. Inspect functional relationship. So what this is saying then is that, right, we've said that pi 1 is equal to some constant. So it's saying that y over gt squared is equal to a constant. All right, what does this do for us? Well, basically, if we wanted to perform an experiment, then all we would need to do is take some object, okay, and if we know how far we're dropping it, and we know gravitational acceleration,
then we can time how far it takes to fall.
So we can perform one experiment with known y and g, or a known, right, we could time, we see how far something falls in a given time. It doesn't matter. We would measure t in this situation, and we would find that our constant is equal to 1/2. So that says that then y over gt squared is equal to 1/2. We can reorganize this to get y is equal to 1/2 gt squared, which looks a whole lot like what's derived early on in kind of trajectory planning physics and dynamics, but without any of the calculus. Okay, so from a purely dimensional analysis approach plus one experiment, we can get to the same thing proposed by Newton. Okay, so that's an example of how we would approach a problem that has only one pi term. Actually, one pi term requires one experiment in order to find a constant. And then that becomes universally applicable to all problems governed by the same physics. For 2 pi terms, okay, things are a little bit more involved. This is when k minus r is equal to 2. Okay. So in a situation like this, we have that pi 1 is equal to some function of pi 2. All right. Which we can think of basically meaning that we could plot this relationship as a single curve on a two-dimensional set of axes. Right? So if we wanted to, let's say we have data that looks like this, or we go out and collect experiments, or perform experiments and collect data. The idea is now we've got, right, we can go out, vary pi 2, right, experiment values of pi 1, and then we can fit a curve to these data. And this curve, right, is an approximation of that functional relationship phi. Right? So this is what we're talking about when we discuss correlation of data. Correlation of data basically is curve fitting to experimental data so that you can estimate values of phi between experimental data points. Right. The idea then is that if you were to go out and you were to fit this curve and you have this data set, then again, any problem that's governed by the same physics can be assessed by using this curve right here. So we'll do an example with this in just a second as well. So correlation from, again, B to any problem governed by same physics. It's important to note here that correlation is useful only where you are interpolating between data. and should not be used to extrapolate data. What I mean by that is, let's say we've gone into the lab and we've collected some set of data that we can then plot in terms of, we can then plot in terms of pi terms. So we've got pi 2, pi 1, and we go ahead and we fit a curve to this. Okay. At this point, we're fine. But if we were to extrapolate this curve, right, we can have no confidence in the values of this curve out here because it's not actually supported by any data. If, for example, we then went back into the lab, we may find that our actual experiments lie along this. So the idea is only trust fitted curves within the bounds of actual experimental values. So as an example on this one, we're going to jump back into our We're going to quickly jump back into our pipe flow problem one more time. So, over the course of the last couple of lectures, we've really kind of beaten this pipe flow experiment to death. But we've established that we've got this dimensionless relationship of this dimensional version of the pressure drop, bringing in length on the left-hand side to some function of what we have now seen to be the form of a Reynolds number on the right, this rho dd over mu. So consider that somebody has gone through and they've collected experimental data for the following pipe flows. So 5 foot lengths of pipe with this one on about 10 foot length. 0.04 feet, I forget what that works out to in metric. But here's pipe diameters and then a 3-inch pipe here with different flow velocities, and what they did was they measured the pressure at each end of the pipe and gave us a pressure drop. Okay, so a very rudimentary set of experiments. The question is now, and these were conducted with water as the working fluid. So we're given a dynamic viscosity, so I should fix that. This is actually it's actually mu, not nu. And the density for water. And we're asked to use this data to predict the pressure drop for pipes also carrying water, but with totally different diameters, okay? Different systems of units and different lengths. So we did a little bit of this when I first introduced the dimensional analysis, but in that case it was saying, all right, we have the conditions first. Let's figure out what experiment we need to perform in order to model those conditions. In this case, we're given an experimental data set. Now we need to find conditions that may or may not match any of those in a dimensionless sense. So let me pull up. Spreadsheet here. And let's see if I can make this a little bit more legible. All right. So we've got here is the same set of measurements that were tabulated on that slide, right? So 5 foot length with that 10 foot length are different diameters, different velocities, the densities, the dynamic viscosities, and the measured pressure drops in pounds per square foot. Okay. I've also just
plug them into a second table down here where they're all converted to metric, but the same measurements.
Right, or the same quantities. So all the lengths are simply multiplied by 0.3048. Pressures to go from PSF to Pascal, multiplied by 47.88, et cetera, et cetera. But the idea is now, in order to make these dimensional measurements that are tabulated applicable to our new set of conditions that we're trying to evaluate, we need to non-dimensionalize them, fit the non-dimensional relationship with some correlated curve fit, and then apply that correlated curve fit to calculate some new conditions of interest. So we do so first, right? We've got the pressure drop per unit length is really the quantity that we need here. So this would be pressure drop divided by the length, right? The Reynolds number is equal to diameter times velocity times density over viscosity. And then this dP, right, the delta P sub L times d over rho v squared is our other dimensionless variable. Get this guy times diameter divided by rho v squared. And we'll go ahead and compute these separately in the metric table over here as well. So let's go ahead and drag these down. Drag these down. Okay, so
note this shouldn't be a surprise, but the dimensionless variables here, the Reynolds number and the dimensionless pressure drop, are the same within round-off error if we compute them with metric quantities, when we compute them with metric quantities as they are with empirical quantities. Right? This shouldn't be a surprise because, like I said, they're dimensionless, they're independent of the system of units you use. There are some small little differences here. Like I said, those just come from the round-off errors and the conversions that are being used. But the idea is we've got our Reynolds number, right, our pi 2, and we've got our dimensionless pressure drop, which is our pi 1 term. And over here, that's a useless way of showing that axis.
Let me go ahead and drag this out of it. There we go.
And over here is a plot of Reynolds number and dimensionless pressure drop. And so these blue symbols are the data points that we've been provided with this experimental data set, now plotted in dimensionless form.
And those of you that are not familiar with Excel's trendline function or trendline functionality, this is a really good tool for problems like this because this allows us to basically try out different curve fits, right, until we find one that approximates the data, right, fairly well. So we've got an R squared of 0.9998, which is, by all accounts, a fairly good fit to our experimental data. And the idea now is that if y is our pressure drop coefficient and x is our Reynolds number, we now have a relationship that we can use to calculate, or at least estimate, the pressure drop coefficient for any Reynolds number that falls within the bounds of our experimental data. So let's come on over here, right, and consider those two other conditions that we were asked to look at, right? This one was supposed to be 2. So there was a 10 and a 20 centimeter pipe, both of them 2 meters long with different velocities, okay, carrying water. We're asked to estimate the pressure drop along those lengths of pipe. So we calculate the Reynolds number for each of these. V times D times rho divided by mu, okay? And then we estimate the pressure coefficient, or the pressure drop coefficient, using this equation right here. So equals 0.1514 times the Reynolds number raised to the negative 0.246. Oops. And what I've done is I've placed these estimated points as symbols on the curve. So we can see that we're within the bounds of our experimental data. Okay. So now I have a dimensionless pressure drop. All that's left is to redimensionalize that. So P over L is going to be equal to this quantity times rho times V squared divided by the diameter. And then the total pressure drop will be the pressure drop per unit length times the length of the pipe. And so we can see then we could go back to whatever customers or engineers are requesting this these data and say for pipe 1 from end to end we'll have 182 Pascal pressure drop. For pipe 2 about a 527 Pascal pressure drop. Oh man. So that's when you have two pi terms. Things get a little bit tougher when you have three pi terms. Okay. So pi 1, some functional relationship, pi 2, and pi 3. Okay. So for a problem like this, if we were to go out and do experiments, we can collect data, right? But what it's going to give us is basically a three-dimensional surface. Or if we want to show it on a 2D plot, right? We could have pi 2, pi 1. We'll basically have pi 3 equals, right, C1, pi 3 equals C2, pi 3 equals C3. Basically a set of curves for different values of pi 3, which would be like slices taken through a three-dimensional surface. This is where things start to get a little bit tougher, right? So, for example, you guys have probably already you've had to use this thing called the Moody diagram for Lab 3, right? Or you've seen this thing called the Moody diagram. If we come back to our pipe flow example, again, oh, maybe. We said, right, the assumption was when we were doing the pipe flow example in the preceding lectures that we were dealing with smooth pipe. If we allowed the pipe to be rough with varying degrees of roughness, then basically that produces another pi term. It adds another pi term that would be take the form of epsilon over d, where epsilon is the height of that roughness. And so what we get in that case is just like I kind of sketched on the last slide. We'll get our 2D axes, right? Reynolds number, pressure drop coefficients, and then we get a set of curves that correspond to different values of this dimensionless roughness. And so it's just a way of projecting this three-dimensional relationship onto a 2D set of axes. For more than 3 pi terms, it starts to get impractical to try to come up with experimental correlations, right? Because then you start getting into higher dimensional space. You have to do a lot of experiments, right? We talked about before. If you have 4 or 5 pi terms, then in order to produce this experimental correlation, you basically start having to perform hundreds or thousands of experiments in order to get a full factorial design of experiments. So for more than 3 pi terms, this is where it starts to become more economical to do model scale testing, and that's what we're going to talk about in the next lecture. For now, it helps to understand the following. Okay. What is the most fundamental? Okay, if we step back, what is the only equation so far, or the only set of equations so far, that apply to every single, at least incompressible, fluid flow we know of? Navier-Stokes. And continuity would be the other one, right? So we've got conservation of mass, conservation of momentum, state form of continuity, and Navier-Stokes. Okay. So most fundamental and universal governing equations. Be Navier-Stokes and continuity. So we're going to go ahead and quickly write these out one more time. I know we're getting tired of continuity. That's du dx plus dv dy is equal to 0. We're only going to consider the 2D case here. And let's go ahead and consider the x momentum equation. Rho du dt plus rho u du dx plus v du dy equal to negative dp dx plus rho gx plus mu d squared u dx squared plus d squared u dy squared. Okay, and we're not going to bother with the y momentum here, because my goal here in writing this out is we want to kind of take a view of what the different terms in here represent quickly. Right, this time rate of change we've already established is what's called the local acceleration, right, of a fluid element, and so this can be thought of as kind of the inertial force, or the local inertial force, let me say. This term in here, because this is what we call the convective rate of change, right? The convective acceleration. We'll call this the convective inertial force. On this side, we've got first is the dx term, right? We determined that this is the surface force due to pressure. This rho gx would be the gravitational body force. And then this last term here we thought of as the viscous surface. Surface force.
Okay, so each term has its own kind of meaning. Right, and it all comes back to, again, if all of this is the MA side of the equation, the A is divided into local and convective terms, and all the S are due to pressure, gravity, or viscosity.
So we're going to skip the derivation of stage here, but if we were to apply the method of repeating variables to the Navier-Stokes equations, the idea is we could non-dimensionalize the Navier-Stokes and come up with some pi terms that basically we could say, all right, now we've got this dimensionless representation. So in order to do a dimensional analysis, it's a little bit different than what we've been doing. Idea is you'd have to pick a set of what we call reference variables instead of just reference dimensions. So for example, we would say V is what we call our reference velocity. P naught would be some reference pressure. And L would be some reference length. Okay, and the choice of these depends entirely upon the problem that's being considered. This may, for example, be, if you have a flowing fluid, it may be the free stream velocity of the fluid. This could be atmospheric pressure, it could be vapor pressure, and this could be, for example, the length of some object that is submerged into a flowing fluid. But what we see then is that using these reference variables to non-dimensionalize the Navier-Stokes equations, we get a set of dimensional or dimensionless variables the Navier-Stokes dimensionless pi terms of the Reynolds number, which is rho V L over viscosity. Okay. The Froude number, which is defined as V over the square root of GL the Euler number, which is P naught over rho V squared, or rather, it's just P over rho V squared. Called the Struhal number. This one's a little bit weird. We'll talk about this in a second. Omega L over V. And then the Mach number is not actually, doesn't actually come from Navier-Stokes, so we'll leave that out for now. So these terms here, okay, can be actually, if we went back and we looked at the terms that go into them, into each of these pi terms, what we would see, and sort of the meaning that we assigned to each of these terms here, okay, we would see that, for example, the Reynolds number can be thought of as the ratio or the relative importance of our inertial forces to viscous forces. the Froude number can be thought of as the ratio of inertial forces to gravitational body forces. The Euler number can be thought of as the ratio of pressure-based surface forces to inertial forces. And the Struhal number can be thought of as the ratio of local unsteady inertia to convective inertia. These are sort of abstract representations, but and it's not terribly important that at this point that you commit these to memory. But the idea here is I want to show you that these common terms that we're going to see, and you'll continue to see as you continue in engineering, are actually based on, they have some physical significance. So we only have a few more minutes, and that's fine because the idea now is to kind of go back through. We started on these slides in the previous. In the previous lecture. We'll try to make another quick trip through these. Okay, so like I said, the Reynolds number. The idea here is that because it represents a ratio of inertial to viscous forces, we know if the Reynolds number is really small. Okay, that basically means that viscosity is dominating the flow. And if it's really large, that means that inertia is far more important than the viscosity. So this video here shows, for example, this spinning up a very viscous fluid at a very small Reynolds number, 0.3, right? And we've got this marker in there that as it stops, the marker basically stops with the flow. There's very little inertia. It's all getting damped out by viscosity. At a higher Reynolds number, we have this sort of continued inertial motion. Okay? And at very large Reynolds numbers, we start to see that viscosity basically doesn't do anything for us. Let's see. I thought it went on to even higher Reynolds numbers. Okay, I guess not. So the Froude number, like I mentioned, because it's a balance of inertial to gravitational force, these can be thought of as the two components that are important to the propagation of waves. And in fact, there's a really cool little example that we're not going to have time to do. But it turns out we can show through our dimensional analysis that we've already covered so far that there's this behavior of waves that we call, that's known as dispersion. That if we applied dimensional analysis, we would find that the ratio of a wave's speed, or that a wave's speed is basically dependent upon the wave's frequency. And this is what leads to the idea that in water, tsunamis, really long wavelengths, travel a lot faster than like small ripples. In solid objects, such as like seismic waves or acoustic waves in ice, the opposite is true, that short, high-frequency waves travel faster than longer waves, which gives rise to this these really weird sounds. How many of you have heard the kind of any like cross-country skiers in the room, or ice skaters, or hockey players, or any of you ever been out on a frozen lake and heard those kind of Star Wars blaster sounds that occurs when ice cracks? That basically occurs, and you can show the relationship using dimensional analysis, but it turns out that Am I not going to get any sound out of this thing? I might not. Okay. Well, that didn't work. There are a few more of these, but I've the primary pi terms there that I wrote down are the important ones to know. The next lecture we're going to talk about when we can't actually, it's no longer economical to do experimental correlations. How do you actually design a model scale experiment in order to reproduce full scale physics? So I'll see you guys on Friday.